Are you ready to harness the power of AI in industrial environments? With the IRIS Foundry Industrial DataOps platform, you can unify industrial data and embrace the potential of predictive and generative AI.
We wanted to make that possibility a reality. With SymphonyAI's Industrial DataOps platform, IRIS Foundry, coupled with generative AI copilots powered by the Azure OpenAI service, these goals are within reach. Combined, these tools offer a unique ability for manufacturing companies to reduce unscheduled asset downtime, improve process efficiency, and enhance connected worker operations. With IRIS Foundry, you can unify industrial data into a trusted and robust data foundation to seamlessly deploy predictive and generative AI solutions. With purpose-built applications to predict downtime events, monitor plant performance, and empower frontline workers, manufacturers can address underlying issues before they impact production. IRIS Foundry can transition you from reactive operations to AI-powered workflows with advanced analytics for trend identification and forecasting, leveraging machine learning to uncover hidden patterns and predict operational trends.
Safe and reliable operations are critical to providing our customers with an uninterrupted supply of the materials they need to run their business, while keeping our costs competitive. Using predictive AI models from SymphonyAI integrated with critical data sources, we have already been able to proactively detect anomalies. With the release of IRIS Foundry, we are excited about the simplicity this will bring to expand the benefits of a flexible AI platform to additional equipment and sites.
Using composable applications available on top of the IRIS Foundry, our customers have saved $250,000 to $1 million per instance of avoided downtime events and decreased maintenance costs by 4%. Those who focused on optimizing their operations have decreased their energy consumption by over 2% and gained more than 3% in their production yield. Additionally, manufacturers have seen their frontline workers increase their knowledge worker efficiency by an average of 34%.
Capture the power of industrial AI to optimize your production with SymphonyAI solutions today.
IRIS Foundry is a composable, AI-enabled industrial DataOps platform that offers the breadth and depth required to scale industrial AI use cases. From the IRIS Foundry landing page, we can see there are 5 key pillars. The first is the idea of orchestration, which is about connecting and transforming IT, OT, and engineering data sources. Once these data sources are connected, they need to be contextualized, which is about building relationships across these different data sources and unifying this data into a unified data model. This unified data model can then be accessed through the AI-powered knowledge graph to analyze asset, process, and performance metrics and power end-user solutions. The Insights pillar shows all the different types of purpose-built applications that can be run on top of IRIS Foundry. And finally, the idea of governance ensures cohesive management and trust within the data that's being used by IRIS Foundry. If we take a deeper dive into the AI-powered knowledge graph, we can see that it offers a digital representation of the operational footprint, along with an ability to drill down to any detail and track any operating parameters. On the left-hand side, we're seeing the asset cortex graph, which maps different types of relationship between equipment. On the right-hand side, we're looking at the performance cortex graph, which allows a rolled-up view of key performance indicators and maps the interrelations between those KPIs. The two graphs are linked, so you can see how performance is impacted by specific pieces of equipment and vice versa. Additionally, the asset performance graph can be filtered to map different types of relationships, such as energy transfer or mass transfer. Also, if you want to be able to compare similar assets, you have the ability to look at different types of assets as well as see how they're trending over time. Finally, the industrial knowledge graph also allows us to access unstructured data types such as reports, documents, and drawings. Now, let's explore the role-based AI Copilot that sits on top of this rich layer of data and knowledge. The Copilot is grounded with a domain-driven industrial LLM and the knowledge graph and is built to make calls directly to the systems of record. The Copilot is trained with specific skills that provide explainability of the results to the end users. In this case, we want to do a more detailed assessment on an alert that was generated from an anomaly detection model on a specific pump. Using the Copilot skills, the end user can initiate predictive analytics and actions from within the same conversation window. In this case, we can see that there are no sensor faults, there are no vibration alerts, and there are no related oil alerts. So we can further this analysis by creating a plot on the key parameter using the analysis skill within the Copilot. The generated plot is dynamic and interactive, allowing users to zoom in on specific areas that they deem might need more investigation. If we want to go further in the analysis, we can also create intercorrelation plots that displays the relationship between multiple parameters of this pump to help identify patterns and determine the appropriate corrective actions. We again call upon the reliability skill to help create these plots. This is just a glimpse of the actionable AI insights that can be achieved through the knowledge graph in Copilot within IRIS Foundry.
So having said that, let me now show you the Foundry application and really focus on the UDM and UNS that Ravi has been explaining. Now, the platform is very, very broad. I'm not going to go into it because it is broad, but I will just highlight the three major components of the IRIS Foundry, which is the DataOps, which is what I will be discussing today and showcasing today. And the DataOps is around data integration and contextualization. Then we have the advanced analytics and AI modeling that allows you to start creating your AI models and machine learning models to run on the data that has been brought in, cleansed, normalized, and contextualized in our DataOps section. And then the insight visualizations and applications. So our DataOps, which is really center and the front of every application that you have today, of every platform that you have today, is the data, because garbage in, garbage out. If you have garbage data, whatever AI analytics you have running will generate garbage analytics, will not be very helpful. So our journey starts with the data integration, where we have data connectors. Now, these are a few samples of the connectors. I'm not going to go into the data connectors and how this works. Again, see that webinar that we did about a year ago that explains how the connectors work. But once we have connection to that data, what we will get from the system are data sources, a list of data sources that have been whitelisted in the IRIS Foundry specific for the project we're working on, or for the enterprise we're working on. Each data source will have information, what kind of data source it is, what is a connector that's bringing in the data, what is the protocol, and just a description. So this is a very basic view of the data sources that we have. Once we have the data sources, we will actually go a bit backwards, because again, we are a cloud tenant. We can run on OT, so we can deploy our platform on OT, but it is a container architecture, microservice architecture of a platform that runs on a server. So this could be OT server or IT server or public SaaS cloud, private cloud, public cloud, etc. So we are going to go a bit backwards. So we're not going to go from the edge up to the cloud, but rather from the cloud down to the edge. So when we're going down, we're starting from our data models. We're starting from our UDM, Unified Data Model. So here we have a list of all of the different schemas that we have for the different source data. So we declared the data sources, but then what does each data source actually contain? So for example, if I would go to, I don't know, let's take Aberdeen Safety Report. So our safety report will have these particular variables or these particular properties. So we have safety incident ID, the date, time, location, reported by, etc. All this information. That's the Aberdeen safety report. But let's go to a different to maybe an Aberdeen QC report or production report, of course, it's going to have different type of properties. So these are the properties per data source that has been imported into the system. But now what happens if I, for example, am responsible for multiple plants, or maybe even within the plant, I have multiple areas, and each area have their own proprietary reporting system. They have their own system. Maybe for some reason, one got it from one vendor, another area got it from a different vendor, and they don't really talk to each other. But now I'm overseeing the entire operations, and I'm getting maintenance reports, maintenance work order from my different plants. So I have from Perth, from my Aberdeen, and from my Arusha maintenance report. I see here I have an ID, but here it's called asset ID for the maintenance report, and here it's called work order ID. So there's no guarantee that the work orders or whatever information we're trying to bring in, whether it is a document, a report of maintenance, quality assurance, financial report, warehouse report, whatever it may be, or even data time series data, there's no guarantee that the naming convention is going to be the same across the board. So what we've introduced is this unified data model, where you can define a unified data model with the properties that you are interested in seeing. Now you declare it, you can add as many properties as you want. You can add links to whatever systems that you want. And then all you need to do is map. So for example, I have a company code. I can go and map this to my division, for example, and say that my company code is division. Now, what does this give me? Is that when I want to access, for example, a maintenance work order from Perth or from Aberdeen or wherever, I don't need to remember that in Perth it's an asset ID and in Aberdeen it's a work order ID. I just need to know I want maintenance work order.id, and I want to get it from the Perth maintenance work order, from that data source. Now, one thing that is differentiating us from, let's say, some of our competitors or some other solutions around UDM, we are not duplicating the code. We are not duplicating the data and blowing up the data storage, but rather this is just a configuration. And then at runtime, whenever you ask for ID, we know what data source you actually want to access, and it knows the mapping. So we have a configuration that is stored, and then we can go and fetch the right key from the correct data source instead of duplicating the data and instead of confusing the references. Then once we have our unified data model, now we can start building our unified application model. Let's open this one, for example. So the application data model is really meant to service a particular application that you wanted to do. So this, when we say application, this could be for predictive maintenance. This could be for optimization of a warehouse optimization, spare part optimization. This could be process optimization. This could be ESG initiative to reduce CO2 emissions, to manage your workforce, to make sure that you have the right skills of the workforce, etc. Each type of application that you want will require different types of data. So what we enable here is to say what kind of data we actually want for this application, and then tie it to the unified data model. And this could be unified data models. This could be specifications, as in time series data that we want, specific sensors. So it's a mix and match, whatever data you require to service this particular application. So once we've set up our unified data model, let's move on more towards our unified namespace, where the data comes into the system. So in the unified data, in the unified namespace, what happens is we're interested in tags. We're getting data. So let's say you have data stored in a database system somewhere, whether it's SAP, CMMS, in the end, it's all stored in some kind of type of database. So it's stored against a tag, against a column in a table, etc. So now we get a definition of all of the data tags that are feeding data from these data sources that we've onboarded, right? And it gives us the information of the unit family, the description, etc. And we have the definition of our namespaces. Each namespace may or may not have an asset hierarchy or information about the assets or a definition of the assets. So for example, you have your CMMS. Your CMMS will most likely have some asset hierarchy that you've already pre-built, showing the hierarchy of that area that the CMMS is serving. So for example, here I have a unit 2. This is a CMMS for WF unit 2. Or it could be a historian where it's a bit broader, a broader scope, where you have the full ISA 95 structure, but may be missing some concept. Like for example, here I have unit 1, I don't have unit 2. And then we have a historian where a different historian that may have a different asset hierarchy and different asset definitions. Now we're going really to the core UNS problem, where you have many different systems, and every system may have naming convention that's a bit slightly different than the other systems. So how do we harmonize it? In the past, what you would need to do is go to your PNID or whatever your source of truth is and start mapping manually. My FW pump 2 is called, I don't know, FW feed water pump 2A in a different system, right? So you need to manually go and do that. But what we've done is we have our assets, our entity resolution. So what we do is we select one of those asset hierarchies, one of these namespaces as our core asset hierarchy as a source of truth. Now, this could be, you can go and create your own asset hierarchy. You can import ISA 95 and manipulate it and manage it to represent your operation, right? So you don't have to start from the namespace, or you can select one of the namespaces to be used as your source of truth that then you will go and expand and add whatever is missing. So we will create an asset hierarchy, but then we still have, so in our case, for example, I did use our Aberdeen CMMS NS as our source of truth that will be used to create our assets. So assets, digital twins, which are here, and I'll go back to this in a second. But for example, I want to bring in my Aberdeen Pi historian, which is not mapped. So let me select all of these and auto map with AI. And what we're doing is we're leveraging our industrial LLM to try and harmonize the different assets that exist in the different namespaces. So what happens is I'm trying to say not only the name, not only based off of the name, but I also want to find the characteristics of the profile of the different assets and tags to understand what does this tag represent. For example, I may have a TI 95 in one system, and I have a TI 9005 in a different system. The AI, if you just base it off of name, might find that it's the same thing. But if one is a time pressure and a time indicator, I don't know why you would use TI for time, but we've seen crazy things before. And another one is a temperature sensor, then it knows, oh, wait a second, although the names are similar, the profile is different, so it's not going to map it. So we map it, and then it gives us the confidence score. I can confirm the mapping, and then everything is going to be mapped. And I can go to my next one, and again, let's try mapping this one. So again, this one was able to map, and it's quite high accuracy because that's the way we set it up. But of course, you may have some cases where the AI mapping confidence is lower than 90%. It could be in the 50s, it could be in the 40s, and in that case, you probably want to have that manual intervention. Now, the key is we understand that there's almost always going to be a human in the loop. AI is only as good as the data that it's trained on. So there's always going to be some areas where it's not going to perform that well, and that's why you would need a human to go and verify that this is correct, confirm mapping, and we're done.